Hi, I'm David. I'm one of the lecturers at the Maths Learning Centre, and this is a rough and ready video about matrices, a lecture basically. I'm going to talk about what matrices are, how they work, and the sorts of things you can do with them, and I'll do lots of examples. So, well, let me tell you, it's pretty mundane. This is the definition of what a matrix is. A matrix is a rectangular array of numbers. Now look at this very importantly. Matrix is the singular. You have one matrix, and matrices is the plural. You have two matrices. English hasn't moved forward enough for us to be able to say matrices yet, but it wouldn't matter if you did. What you don't want to say is matrice. That's not a thing. It's one matrix. Okay, so a matrix is a rectangular array of numbers. So for example, they could look like this. Okay. I've got 6 numbers here, 1, 0, minus a third, 3, 7, 6, 1, 0, 9, and they're in a rectangle. And we tend to put square brackets around them, but you're allowed to put round brackets. What you're not allowed to do is not put anything. Okay, you have to put some shape of brackets, and they both have to be the same kind. So there's nothing stopping them from being square. You're allowed to have the same number across as you do down. And there's nothing stopping them from being very large. And they can have any numbers at all in them. They can be square roots, they can be fractions, they can be big, they can be small, they can be negative. Doesn't matter. Any numbers at all are okay. And just to point out to you that a rectangle is allowed to only be one wide, and so you can have them this way. And this way. And in completely technical sense, you are allowed to just have a 1 by 1 matrix, which just has a single number in it. These are all matrices. And seems pretty boring. Why would you do this? Well, it is boring when you do it that way. The only thing that makes matrices interesting is what we have done in order to turn them into something interesting. So as a mathematician, I've created a new mathematical object. It's a collection of numbers that are in an array like this, and that mathematical object ought to have some properties. Numbers are mathematical objects, and they can do addition and multiplication and division and various other things. And I'm so familiar with how those operations interact with each other that I can have rules like the distributive law, that I can expand out multiplication over addition inside brackets, that sort of thing. And I can use those rules even when I don't know what the numbers are, and I can use letters instead to stand in for numbers that I don't know or I don't want to know. And I'm going to do the same thing with matrices. I already did it in another video for polynomials. I talked a little bit about how you can add them and multiply them and that sort of thing. And we're going to do the same thing here with these new types of objects. Of course, they're going to borrow some of their properties from the numbers themselves that they're made of. Right. So that's the idea, and mathematicians are really interested in this sort of thing. And anytime a new object is created, it's a useful thing to sit down and go, well, what operations can I do with it? And how do those operations interact with each other? How do I calculate them? And how do I talk about them even if I don't know what the matrix is? And essentially what we're going to do is we're going to create an algebra for matrices that's similar to the algebra for numbers, but a little bit different. And there's going to be a couple of new things that we can do to matrices that we couldn't do to just plain numbers. So that's the story. Just so you know, matrices were invented about 100 years ago, late 1800s, early 1900s. And they were invented to keep track of the coefficients in linear equations. So in an equation like 4x plus 5y minus 7z equals 6, those numbers that are next to the x, y and z are kept track of with a matrix. And they borrow some of the things that we do from the linear equations. But that's not a topic for today. We can talk about that. There should be another video soon somewhere about linear equations that you can have a look at. Okay. So, I'm going to have to talk about some features of these matrices in order to make sense of some of the addition, multiplication and whatever stuff. So I'm going to need some terminology about what the matrices look like and the pieces that they have so that I can do the things I want to do. So I'm going to start there. So the features of a matrix. The first feature is the entries. Entry is the word for one of these numbers that's inside a matrix. So are the numbers inside the matrix. They're called entries. And so I can say that this matrix has entries 6 and 6 and 7 and 0. They are the entries. And it's useful to be able to tell someone which entry you're talking about. So if your matrix has several, it's a rectangle and you want to talk about, say, this one, it's useful to tell them that it's in row 2, position 3. So we number the rows going down and the columns going across, and you can say which entry it is. So entry ij, that's what it's called, is in row I counting down. And position j counting left to right. Okay. So for example, in this matrix, just going to copy one of the ones I had before. Entry 2, 1 is minus a third, so it's in row 2, position 1. And entry 3, 2 is row 3, position 2, 109. Now you can do that the other way around. You can say, well, entry 2, 1 is in column 1, position 2. That works just as well. But I find it easier to talk about the rows and which position within them. And I've already mentioned something sort of implicitly that is important to talk about. So the next thing to talk about is rows and columns. So these vertical pieces of the matrix are called columns, and these horizontal pieces are called rows. There's no word for it. It's horizontal strips. Vertical strips. I mean, those words, rows and columns, already exist for tables in, say, an Excel file. So we sort of use them for matrices as well. And just as an example, in the matrix 5, 5, 7, 6, 0, minus 1, 8, 5, 3, 4, 4, 8. Row 1 is, well, let's say row 2 is 0, minus 1, 8, 5. And column 3 is 7, 8, 4. So the rows are numbered from the top down, and the columns are numbered from the left to the right. This is just going to be useful for me to be able to talk about what's going on when we do these matrix operations later. So the last feature of a matrix that belongs to all kinds of matrices that I want to talk about is the size. So sure, we might be able to talk about the individual entries and be able to pick out exactly which one we want. And sure, we might be able to pick out the columns and the rows. Well, overall, you might want to describe how many rows and how many columns there are. And so you can say a matrix with m rows and n columns is said to have size or order m, and this is pronounced as m by n. Now it's not n times n. You do not calculate these two numbers and figure out what you get when you multiply them. I mean, you could if you wanted, but when you say the size of a matrix, you have to say how many rows it has and how many columns there are. And it's worth pointing out, after I've done an example, and you could say this is a 3 by 2 matrix. So sometimes you don't even say it has size 3 by 2. You just say it is a 3 by 2 matrix. So that's how it's done. And I just want to point out a couple of things. This is a 3 by 1 matrix, for example, and all other ones you can do as well. 4 by 1, sorry. Okay, so let me point something out. We can already say something. Every row of an m by n matrix has n columns. So every row of this 3 by 2 matrix has 2 entries in it. And every column of this 3 by 2 matrix has 3 entries in it. So that's useful to know. Every column of an m by n matrix has m entries, and there are n columns in total, and every row of an m by n matrix has n entries. Not important really, but I just wanted to say it because it might be important at some point. So those are the pieces of a matrix that's going to allow me to talk about some stuff. There are some common matrices that have names, but I may mention them later. There is one last piece of a matrix that's worth pointing out, and it's called the diagonal, but it only works for matrices that have the same number of rows and columns. So in an n by n matrix, actually before I say that, it's probably worth pointing out, just as a piece of terminology, an n by n matrix with the same number of rows as columns is called a square matrix. That's an important thing to know. I really shouldn't have put a box around it. I haven't put boxes around anything else. But anyway. Okay. So the last thing that you might want to find in a matrix is called the diagonal. And so in a square matrix, The diagonal is positions, is entries 1, 1, and 2, 2, and 3, 3, etc. That's what the diagonal is. So, for example, has diagonal 3, 6, and minus 6. And the diagonal is right here. Okay, so these are going to become important for talking about stuff. And I'm going to leave that there. Okay, now we've got this terminology, we can start using it to describe how some of these things work. So, there are operations that we might be able to do to matrices, because we're going to borrow them from numbers, and we can do them whenever we can do them. And sometimes we can do them and sometimes we can't. So we can say operations. So the first operation is addition. We learned how to do that early on. So in addition, when you add two matrices, you add their matching entries. Add the entries in matching positions. So what that means is that the entry in position 1, 2 is going to be the same as the entry, and you're going to position 1, 2 of the first matrix plus position 1, 2 of the second matrix will produce position 1, 2 of the third matrix. Okay, and so just as what that means is that you can't do it unless every entry in one has a matching entry for the other. So they have to be the same size. So for example, this thing here, these two matrices are the same size because every time I want to add something to the other, they have a matching entry to do it, and I can literally just add them. 1 plus 8 is 9, 0 plus 7 is 7, 3 plus 6 is 9, minus 7 plus 6 is negative 1. And that's how you add matrices together. Seems pretty natural that you would want to do such a thing. But just as another example, this doesn't exist. Because while I can add this to this, and this to this, and this to this, and this to this, I've run out of entries to add to here. And so that doesn't exist. It can't be calculated. There is no thing that is the addition of those two things. You can't even actually write it at all. And it doesn't make sense to put a plus there. Okay, because they're different sizes. Okay. Subtraction is similar to addition. You just subtract the matching entries. Can only be done if they're the same size. Okay. So now we could do some fun games where you could say, well, think of a matrix, a different pair of matrices that adds up to 9, 7, 9 minus 1. and there are infinitely many possibilities that you could choose, and matrices do just add that way. Okay. All right. And subtraction is the same. But to be fair, back with numbers, subtraction wasn't all that different to addition. They're at the same level in the order of operations. You do them in whatever order they come. At this stage, it's going to be helpful to be able to start to know the rules of how these things work when you combine them with each other. Okay? So, and in order to describe those rules, I'm going to need to give letters to unknown matrices and letters to the unknown entries of unknown matrices at some point. And so it's worth pointing out at this stage that when you want to refer to a matrix, an unknown matrix, or even a known matrix, when you want to refer to it, you normally use a capital letter, and we use small letters for ordinary numbers. For unknown matrices, and small letters for numbers. That's the tradition. There's nothing stopping you using a small letter for a matrix, but it will confuse the people reading. And also, definitely, you cannot, if someone uses a big letter, you cannot use a small letter when you're talking to them about that thing. If I have said capital A is the name of a matrix, you must, in all of your writing, call it capital A and not small a. That's important. Maths is case sensitive, just like your password in your computer. Okay, so we've got addition and subtraction, and it's useful to know some things about addition and subtraction of matrices. So here are some rules so far. When you add two matrices, matrix A and a matrix B, if it's possible to add them, obviously. If it's not possible, then nothing happens at all. Then it's the same answer as when you add them the other way around. Okay? But subtracting is different. Okay? So A plus B is equal to B plus A. They are the same answer as each other, but A minus B is not equal to B minus A. You can't just, and that's the same for numbers, right? 2 minus 3 is not the same as 3 minus 2. One of them's negative, the other one's positive. Okay, so there's some rules. And we can start to make other rules about these things. But I'm going to now do one thing that you might not have noticed over in maths, and we're going to do it here over in ordinary algebra, and we're going to do it here in matrices. I can say, well, there is a matrix for every size that you can add without changing the answer. Okay? And this is the appropriate place to have this special matrix. So, so it's sort of like it's called the zero matrix. So, for every size, the matrix with all entries 0 is called the zero matrix. And there's one for every size. There's a 3 by 2 zero matrix, there's a 4 by 4 zero matrix, there's a 1 by 7 zero matrix, there's a 6 by 1 zero matrix. And normally we use the capital letter O for the zero matrix. And you might be saying, Just a second, David. How can you say the zero matrix? There's all these different zero matrices. Well, in context, you will be able to tell how big your zero matrix is, because if I attempt to add it to something that you know is 2 by 3, well, it would have to be 2 by 3 if that addition was worked at all. So we use capital O for the zero matrix, and it has the property that if you add it to anything, it doesn't change the answer. Okay, which makes sense. You're adding 0 to everything, it's the same. So A plus O is not O, it's A. For any A, as long as they're the right size. So we're used to that. The number 0 did that for numbers, and we have a zero matrix for matrices. So we're working through things. We've got addition, we've got subtraction. Now we have, there's a word for it, it's called negation. We have the minus of a matrix. So the definition is that if you have a matrix called A, you can have minus A, and that is the matrix that you would add to A to get the zero matrix. So minus A is the matrix such that A plus whatever minus A is comes out to the zero matrix. Now that seems like a weird definition, but that's technically the definition of the number minus 3. The number minus 3 is the number that you would add to 3 to get 0. The point is that when you add negative numbers, it takes you down to 0 from whatever the number is. But it turns out that minus A is the same as A, but with all of its entries minused. So if the ij entry of A is A, then the ij entry of minus A is minus A. And that deserves an example. If A equals 1, 0, 3, 7, 6, minus 8, like that, then minus A is, well, just minus all of them. Now minus 0 is still 0, and minus 8 is plus 8. So it's not like they all become negative, they all become the opposite of what they were before. Okay, so you can start to think of negation as subtraction as just adding a negative if you want, but it's not like there are negative matrices, because this matrix has some positive numbers and some negative numbers. There's no such thing as a negative matrix, but every matrix has a negation. It has a minus A. Okay, so this is all right. I mean, at the moment, these are all being done with individual sizes of each matrix. And so at the moment, these operations all live inside a particular size. You can do addition and subtraction and negation and zeroing with matrices that are 3 by 2, and you have lots of 3 by 2 matrices playing with each other. And you have addition and subtraction and negation with 5 by 7 matrices, and all these matrices play with each other, and that's great. But there are going to be some things that are going to make matrices of different sizes interact with each other. Okay. Let me just check my list of things that we can do. All right. Now, we are going to define a brand new thing that didn't exist with numbers. Well, it sort of did. So with numbers before, when we did A plus A, what we got was the same as 2 times A. Now, number times matrix might be a bit of a weird-ass thing to do, right? Because so far we've only had matrices interacting if they're the same size. But we can define what that means. So we're going to have to borrow some things from our old understanding of numbers and try and make them work for matrices. So this is called scalar multiplication. The word scalar is a fancy word for a number which scales something. When you multiply by 7, you make it 7 times bigger. And you can imagine that being a scaling, changing the scale of a map. That's where it came from. So scalar multiplication is borrowed from the idea that a plus a for numbers is 2a. And so a plus a for matrices is also the same answer you would get of just multiplying all the entries by 2 because you just added them all to each other. But we can even do it even if they're fractions or any other numbers. And we can just borrow that idea and say, well, number times matrix is the same as number times every entry. So given number k and matrix A, Ka is the matrix whose ij entry is k. Just a second, that's too hard to say. Where's my eraser? Seem to have lost it. Oh well. If A has ij entry little a, then Ka has ij entry Ka. So basically, every entry of one matrix, you multiply it by the number k, and that is k times a. So here we go. Just as an example, if A is this matrix, then I can multiply that matrix by any number I like. So 2A will be multiplying everything by 2. 6. Half times 2 is 1. 7 times 2 is 14. 6 times 2 is minus 6 times 2 is minus 12. 4 times 2 is 8. 2 times a third is 2/3. So to get to 2A, you multiply everything by 2. But it is the same answer as A plus A. And like a half A would be a half of 3, a half of 2, a half of 7, a half of 6, a half of 4, and a half of a third, which would be a sixth. So it works for fractions, it works for negatives. Minus 6A would be 3 times minus 6, a half times minus 6, 7 times minus 6, minus 6 times minus 6, which is plus 36, 4 times minus 6, minus 6, a third times minus 6. Okay? That's what it means. Okay. So just some rules. We know that there are some rules. And the rules go, we can start to see how these operations interact with each other. So now that we've seen addition and negation and scalar multiplication as well, we can start to see how they interact. And so some rules are that k times a plus b, I can expand scalar multiplication out like I did with ordinary multiplication back in the day. And also, k times m times a is the same answer as multiplying those two numbers and then multiplying by a. Now just note, when we write these things, we never write the k on the right-hand side. It's just tradition when you do scalar multiplication to always do k on the left-hand, the number on the left-hand side. So we never write it on the right-hand side. That's just not how it's done. Okay, so there are our rules so far. They're sort of distributive law here. We also have some useful things. We know that it'll be the same answer if you do minus a, it's the same answer as minus 1 times a. And the reason I say that, it seems like a stupid thing to say. You say, well, David, obviously, but it's not obvious at all, because minus A is defined as the thing that you add to A to get the zero matrix, and minus 1A is the thing that you multiply every entry of A by minus 1. And at the moment, they have two different definitions. And we have to be sure they really are the same matrix. And the only way to be sure is to make sure that every entry is the same. Now, all the entries of this are minus what they were before. And all the entries of this are minus 1 times what they were before. And they are the same thing. And so they really are the same matrix. And I should just point this out right now, that minus A plus B, well, it's minus 1 times this, so we can use this rule to bring them in. That's the same as minus A minus B. And all of our rules for dealing with minuses, with subtraction and scalar multiplication, are going to apply to matrices as well. Okay, so we're doing well. We can now do some neat little proofs if we want. We could prove, if we wanted, that A plus A was 3A, because currently they have different definitions. But it's fairly obvious that that one is true to most people, but still, as I said, not really obvious from a mathematician's point of view. You have to convince people based on the definitions what's going on. So I could totally prove that. I could totally say, for 2 by 2 matrices, A, prove that A plus A plus A is 3A. Okay, and you might look at that and go, well, duh, but that's not the definition of what these things are. A plus A is a different thing to 3A. So here we go, we're going to prove that they are the same. The easiest way to do that is to give letters to the unknown entries of A. So I'm going to say for numbers A, B, C, D. Because I want it to show for all 2 by 2 matrices, or for any 2 by 2 matrices, and in fact I should say for any 2 by 2 matrix A, prove that A plus A plus A is 3A. Now, you might think that when it says for any 2 by 2 matrix A, that you can just pick the one you want, because it says any. But when a mathematician says prove this for any, it means prove this for all of them. And so we have to prove that it's true no matter which A we pick. And so we are going to pick some letters to stand in for any number that we could have thought of. So let A be A, B, C, D for numbers A, B, C, and D. And you have to tell people what the letters stand for when you do this sort of thing. And then we can go A plus A is A, B, C, D plus A, B, C, D plus A, B, C, D. And then if I add these two together here, well, I can add them all technically. At the moment, we haven't actually established the fact that you can add these two and then these two, but since I can add them in any order, it should be fine. And so that's going to be A plus A plus A, B plus B plus B, C plus C plus C, D plus D plus D. And now these are numbers, and for numbers we do know that A plus A is the same as 3A. And we do know for numbers that B plus B is 3B. And this is the same answer we would have gotten if we had done 3 times A, B, C, D, which is the same as 3A. So we have proved it. We have proved that A plus A is the same as 3A. And this is one way of doing working like that. You can start at one end, do working until you notice the thing you were aiming for, and you get to the end. These equal signs say that this is the same, so I read this loud, A plus A equals matrix plus matrix plus matrix, which is equal to this matrix, which is equal to this matrix, which is equal to 3 times this matrix, which is equal to 3A. And each of these is read aloud as which is equal to. And it tells the reader that you're just working on the same object and just writing it in new ways on each line. Okay, So, what have we done so far? We've talked about addition, we've talked about subtraction, we've talked about the zero matrix and negation, we've talked about scalar multiplication, and we've seen some rules about how those things interact with each other, and we've been able to do a little matrix proof based on the individual entries of the specific size of matrix I was thinking of. Okay. All right. So what have we got? We've got addition. All right. The next thing on my list for numbers would be multiplication. Now, multiplication is a whole other story. You don't just multiply the matching entries of the two matrices. Nope, that is not how multiplication works. And the reason it doesn't work that way is because matrix multiplication was borrowed from matrices being used to represent equations. And so we have to do matrix multiplication this way, or it doesn't help us do the thing that matrices were designed to do. So matrix multiplication is quite different to really anything that you would expect. And the fundamental thing it's based on is that a row times a column produces a single number. Okay? So this is the basic idea. A row times column equals a single number. That's the basic idea. And this row has to have the same number of entries in it as this column. Okay, so it's easier to see with an example how this is going to work, and bear with me. So the basic idea is this. So an example, and I haven't told you specifically how this happens, but what you actually do is you multiply the matching entries of the row and the column, and then you add up the answers, and that's what produces the number. But they don't match in the same way as they used to because they're not in exactly the same position, but that's the idea. So multiply matching entries and find the total. Okay, so for example, 1, 0, 3, 7 times 5, 8, 2, minus 1. Okay, do you know what? I'll just change some of these numbers. There we go. 1, 0, minus 3, minus 7, and 5, 8, 2, minus 1. Just so you know, when you're writing them as rows, it can be a bit tricky to see whether you've got numbers or whether that's supposed to be addition, so we tend to put commas when it's a single row by itself. So this matrix multiplication, row times column, should be a single number. Okay? And the way that it works is you will take each entry and its matching one. So the first entry of this from the side and the first entry of this from the top, and you'll multiply them by each other, and then you'll do that for all of them. Okay? So 1 times 5. Just a second, I just need to get something. Okay, I found it. Found the thing I needed. Okay, it's just a useful device to help me here. So the first entry and the first entry here, they together produce 5. And then the second entry and the second entry, 0 times 8. And then the third entry and the third entry, is minus 3 times 2. And then the last entry and the last entry is minus 7 times minus 1. And we add all those answers together. So we have 5 plus 0 minus 6 plus 7, and so we end up with 6. So minus 6 plus 7 is negative 1, 5 minus 1 is 6. Okay, that's what happens when you multiply a row and a column. You get a single number. Technically it's a 1 by 1 matrix, so I should probably have square brackets around it. And that may seem really complicated, but it has to do with having certain number of objects. It has to do with beginning this process with problems where you had this one is keeping track of the size of things, and this is keeping track of how many of each thing you have. Now the negatives might be difficult, but it's about debt and profit and loss and that sort of thing. Okay, so that is the fundamental basic idea of matrix multiplication. And what we do is when we have a bigger thing that's got more rows than this and more columns than this, is we do it for every row and every column. And we make a new matrix that keeps track of all the row by columns. Okay? And so what that means is the only way it's possible to do matrix multiplication is if the rows of the first matrix have the same number of entries as the columns of the second matrix. So for full matrix multiplication, so what we do is we take the rows of the first matrix, row I of the first matrix, times column J of the second matrix, is entry ij of the answer. That's how it works. That's how matrix multiplication works. And it only works when the number of entries in the rows of the first matrix equals the number of entries in the columns of the second matrix. Because otherwise we won't be able to do this operation. Okay. So just to point out, the number of entries in the rows of the first matrix is the same as how many columns the first matrix has, and the number of entries in the columns of the second matrix is the same as the number of rows that the second matrix has. But I find it much easier to remember that this is working the way it is by referring to the entries in the rows and the entries in the columns. And that's because I use the entries in each row and the matching entries in each column to figure out the answer. So here we go. I'm going to need to actually show you how the matrix multiplication is done. And I'm really hoping that this works out to something good, because it's going to be awful if it doesn't. Yep, I'm just going to change right. This is going to be my matrix. I was just avoiding the answer coming out to a fraction. There's actually nothing stopping the answer coming out to a fraction, but I just wanted to not have to do some fraction arithmetic while I was showing you what to do. Okay, so each row of the first matrix is going to have to be multiplied by each column of the second matrix. And I will do the whole thing in full glory. We have plenty of space to figure out what's going on. Might even need more than that. Okay, so I'm going to get my little plastic sheet so that I can do this. So I'm going to take the first row and the first column, and the first row and the first column are going to produce the entry in the first row and the first column of the answer. So the first row will be 1 times 8, which is 8, plus 0 times 3, which is 0 times 3, plus 7 times 0, that's the next one. That's what goes in that position. Okay, so I've done the first row and the first column. I'll stick in the first row and do the second column now. So 1 times minus 10. I'm just going to put a comma there. It's okay to do that if you need to. And then we're going to have 0 times a quarter. And then we're going to have 7 times 2. Okay, now I've finished the first row. I'll start doing the second row. And first I'll do it with the first column. So 1/2 times 8 plus 16 times 3 plus minus 8 times 0. So I just shortcutted that. I did 1/2 times 8, 16 times 3, minus 8 times 0. And I'm still in the bottom row, and I'll move this over to the next column. So I have 1/2 times minus 10 plus 16 times a quarter minus 8 times 2. So basically you stay in this row and do both of these columns, and then you do this row and do both of these columns, and if there was a third row you do this and both of these columns, and you could have as many rows as you wanted here and as many columns as you wanted here, as long as all of these were 3 and all of these were 3, it would still work. Of course, you know, as long as these all have the same number of entries and these all have that same number of entries, it'll work. And then you figure out what these answers are. And so we get 1 times 8 plus 0 plus 0, which is 8. 1 times minus 10 plus 0 plus 14, which is minus 10 plus 14, which is 4. Half of 8 is 4. 16 times 3, 48. And so 48 plus 4 is 52. And 1/2 times minus 10 is minus 5. Plus 16 times a quarter, that's 4. So minus 5 plus 4 is minus 1. Minus 16, so minus 17. And this is the answer we get. And you cannot tell from this that it came from there. Matrix multiplication is a bit mysterious, and a whole lot of stuff is going on at once when you do it. So if you do want to really multiply it out, you're going to have to do it one piece at a time. It is okay to not write this bit here. Most people do that bit in their head and do it as a running total. So I do need to say something. It is possible to multiply things that are pretty small. So for example, this, for example, is totally possible because, nope, it's not. So I'll just say this is not possible. It's not defined because the number of entries in the rows in the first matrix is not the same as the number of entries in the columns of the second matrix. The rows of the first matrix only have 2, the columns of the second matrix only have 1. And let me show you something. This is totally possible. The rows in the first matrix are the same as the columns in the second matrix. Totally. Can completely do this. And so we can do this. So row 2 and column 1. 2 times 1 is 2, but there's no other things to add, so that's okay. Row 2 and column 2. 2 times 1 is 2. Row 1 and column 2. Row 1 and column 3. 2 times 5 is 10. Row 2 and column 1, 0. Row 2 and column 1, 0. Row 2 and column 2. Sorry, row 2 and column 1, 0. Row 2 and column 2, 0. Row 2 and column 3, 0. Row 3 and column 1, 3. Row 3 and column 1, 3 times 1 is 3. Row 3, column 2, sorry. Row 3 and column 3, 3 times 5 is 15. It's hard for me to verbalize that because I'm just doing it spatially, so it's difficult for me to keep track of what thing I'm actually pointing at. So it is totally possible to figure out what figure out a matrix multiplication if one is a row and one is a column, if they're the other way around than you normally expect. And in fact, this could have been as long as I wanted. I could just as easily have had like a -2 here. And I would go row 1 and column 1, row 1 and column 2, row 1 and column 3, row 1 and column 4, row 2 and column 1, column 2, column 3, column 4. Row 3 and column 1, column 2, column 3, column 4, and that would be okay. All right, and it's because the rows and the columns have the same number of entries in them. All right, that's matrix multiplication. Now, since it is so extremely complicated, matrix multiplication has some serious problems with it. That mean that we can't do as many things as we used to do when we had we can't really do when we had just plain numbers. And so there are some rules. So if you multiply A and B and then multiply by C, you do in fact get the same answer as if you do it this way. But there's something extremely important. When there were numbers, ABC was the same as ACB, which is the same as CAB, which is the same as BAC, and it didn't matter what order you multiplied them in. You could rearrange that order and multiply them whichever way you wanted. Not true for matrices. So I just want to tell you, this is called the Associative Law. Okay? But if you have A times B, it is totally not the same thing as B times A. For a start, it may not even be possible to multiply those matrices on both sides because the number of rows and the number of columns may not match up correctly both ways. Secondly, even if you can multiply them both ways, it may not even be possible they may not even come out to the same size matrix. If you've got a 3 by 2 matrix and a 2 by 3 matrix, it'll turn out to be a 3 by 3 one way and a 2 by 2 the other. And even if they both were the same size, they're almost never the same matrix. The entries are different. Now, this last rule I just wrote is so important that I'm going to do a specific example of it just to prove it to you that it doesn't always work. And to prove to someone that something doesn't always work, all you need to do is show that it doesn't work once. So just so you know, normally if they are equal, it's called the commutative law. And so we're going to actually say that there is no commutative law for matrix multiplication. Okay, I'm just going to really, really ram home that this doesn't work to you. So for a start, let me pick some matrices. I'm going to call this one A. I'm going to call this one B. So A times B is totally possible. I will not actually calculate this. That's why I've been so free and easy with having so many big numbers in it. This is totally possible to calculate because these rows have the same number of entries as these columns. And that's okay. You can always multiply matrices if that happens. And so this is okay. But BA would be attempting to do this. And these rows have a different number of entries to these columns. And so it's not actually even possible to do this. So in this case, AB is not the same as BA because, well, AB is possible and BA isn't even possible. It doesn't even exist. So AB is not equal to BA since BA does not exist. Okay, but how about if there actually are both possible? So what if A was 0, 1, 3, 5, and B was minus 6, 7, 2, 1? And it probably doesn't matter. I'm not even trying. If I just put random numbers in there, it is extremely unlikely to work both ways. So AB is this. So let's see, 0 times minus 6. It might just be easier to just do it one more time since you've only just learned how to do this. 0 times minus 6 is 0. 1 times 2 is 2. And so if I add them two together, I get 2. So I was in the first row, and now I'll do the next column. 0 times 7 is 7, is 0, and then 1 times 1 is 1, so 0 plus 1 is 1. So now I've finished with the first row. I'll do the next row, and I'll go back to the first column. 3 times minus 6 is minus 18, and then 5 times 2 is 10, so minus 18 plus 10 is minus 8. And 3 times 7 is 35, and then 5 times 1 is 5, and so we get 40. So that's what we get when we multiply them this way. But BA is this way round. So now I've got minus 6 times 0, which is 0. 7 times 3 is 21. I get 21 in this spot. Already my matrices aren't equal. I can tell just because the first entry of both of them isn't the same. They are not the same matrix, even before I calculate all the rest. Minus 6 times 1 is minus 6. 7 times 5 is 35. 35 minus 6 is 29. 2 times 0 is 0. 1 times 3 is 3. 2 times 1 is 2, 1 times 5 is 5, and 2 plus 5 is 7. These two matrices are totally different, even though it's possible to calculate them both. Now, I do want to say something. I've been very careful in my process of writing these things down. I haven't just written this without the AB. It's important to me to tell the reader that AB works out to this and BA works out to this, so that at the end I can say that AB is not BA. Because if I'm going to make a statement about the matrix AB, somewhere I should write down what the matrix AB is. So it's not really good enough from a writing perspective to just leave that bit out. And secondly, I have gone all the way to figure out what AB is, and I've gone all the way to figure out what BA is. What I didn't do is start with AB equals BA and figure out both sides and then find out that they weren't equal. I can't really declare anything equal unless they really are. And so since I didn't know whether they were equal until I calculated them first and then I decided if they were equal. Okay. So if someone, say, writing in, who gave you an assignment or an exam, asked you, confirm that the commutative law does not hold for matrix multiplication, then you could do this. Because, well, not holding means that there's just at least one example where it doesn't hold. But as I said to you, if I thought of almost any random pair of matrices, they would almost never commute. That's what it's called. I should point out that sometimes they do. It does sometimes happen, it just very rarely happens. Okay. All right, now where was I? I was in the middle of doing rules. So we've done addition and we've done scalar multiplication and we've done negation and now we've done multiplication. We should figure out how it interacts with all those other things. So multiplication interacts with addition the way we expect it to. So we know that A times B plus C is the same as AB plus AC. Now I have to point out, even writing this statement here, there's a lot going on that most matrices you wouldn't be able to even do this. You're going to need B and C to be the same size matrix so that you can add them, and then you're going to need them to have the same number of entries in their columns as A has in their rows. And so it's going to be quite difficult to find matrices that do this, but if they do this, then they will also do this, and it will be the same answer. And it works on the other side as well. We know that matrix multiplication is different on either side, but it turns out that the rules are the same on either side, even though the answers come out to different answers. So I should just point out that these are not the same thing, and that BA is different to AB, and CA is different to AC. It's not impossible for all this to turn out to the same answer after all, but you know, it would be extremely rare. Okay, so we know how it interacts with addition. How does it interact with scalar multiplication? Let's see, if you had Ka then times B, that's going to be the same as K multiplying the AB first and then times the K. And it also works the other way. If you've got times KB in the middle, then this will be the same as this too. So you can pull out constants that are multiplied, like the scalar multiplication, anywhere you want, and you can move it around wherever you like, and it'll work out to be the same answer. This one's quite nice, actually. And that means that we don't normally put the brackets here. We just write it as, you know, KAB. Because it doesn't really matter what order you do those things in, it's okay to leave out brackets and that sort of thing. But traditionally, you would normally do the AB and then the times K, because the sort of matrix multiplication feels stronger and bigger than the scalar multiplication. But there's no particular order you have to do it in, because this rule says that it works. Did we have anything else? Not really, because sort of our negation of minusing things sort of worked out with this anyway. And so that means that we can now do matrix algebra with both multiplication and addition, and we can do things like, well, we can expand brackets and stuff. And we can factorize. It does work the other way. Yeah. Okay, I'm just going to look at my examples. I did have an example I wanted to show, but we need to learn one more thing about the way that matrix multiplication works before we do that. Actually, two more things. So the first thing I want to do is remember how when we did addition, there was a special matrix that we could add to anything and it wouldn't change the answer, and it was the zero matrix? Well, there's one for multiplication too. So it made sense with addition that if we wanted to add a matrix and not do anything, we should have 0 in every entry, because you're going to add 0 to everything and that doesn't change. But the matrix multiplication is a little more, well, it's just more. And so it's going to be harder to do this. So there is a matrix that you can multiply onto. For any matrix, there is a matrix you can multiply on the left and a matrix you can multiply on the right that won't change the answer. And it's called an identity matrix. And just like with the zero matrix, there's one in every size, only it turns out they have to be square in order for it to do its job. And so that's where I am now. Okay, so have an identity matrix, and the identity matrix does this. So an identity matrix I has the property that I times A is A for all A where this is defined. So that's an identity matrix, and I say an identity because there's one for all different sizes. There's one that's, that works for matrices that have two columns. It also works this way, or and AI is A for all A where this is defined too. So I should just put a B here just to make sure that show that there might be different matrices. So that's sort of what the identity matrix sort of is. That's what it's designed to do. It's designed to, when you multiply it by other matrices, it doesn't change the answer. And it turns out the only way to achieve that is to have something that has ones down the diagonal and everywhere else. So it's a square matrix. So remember I said earlier that I needed to tell you what a square matrix is. Now you know why I needed it. An identity matrix has to be a square matrix, which means it's got the same number of entries in its rows as it does in its columns. And it has to have ones down the diagonal and zeros everywhere else. One in the diagonal entries. And zeros everywhere else. I will say zeros in every other entry. All other entries. So for example, you could have a 2 by 2. You could have a 3 by 3. You could have a 4 by 4. Like that. Oh, I think I've missed a 0. There we go. Okay, these are all different sized identity matrices, and we normally call it the letter I for identity, and the identity is actually technically an identity for multiplication. And it's called identity because if you multiply it by A, it will tell you what A is. It tells you the identity of the matrix A. If you really want to specify exactly which identity matrix you have, you can put a little number next to it to say which size it is. So you can say this is the identity matrix of size 2, and this is the identity matrix of size 3, and this is the identity matrix of size 4. But usually in context, you will know what size it is by the matrices that it's attempting to multiply by. And so you don't really usually need to specify unless you're being extremely careful. Okay, that's the identity matrix. And the identity matrix is a great matrix. I can multiply it wherever I want and it won't change the answer, which means that sometimes it's useful to put it in where it wasn't before to make things a little easier. And the last thing that we're going to do, so just a second, we have done addition, we've done subtraction, we've done multiplication by a scalar, which normal numbers didn't do, and we've done multiplication, which was a bit funky, and we've got an identity for multiplication. There is one more thing to do, which is powers. So matrices, numbers had powers. We could raise it to an exponent, and so we could have like 5 to the power of 3, and that would be 5 times 5 times 5. And we want to know if, but we were also able to do things like 5 to the power of a half, which is root 5, and we're wondering if we can do that to matrices, because we're trying to copy what we do to numbers to these new algebraic objects. So let's give it a go. I feel like I should, before that, just prove to you that the identity matrix really does what it does. So let me just, sorry, I am roughly half making this up on the spot, so just bear with me. So if A is equal to 1, 3, 2, 5, 0, 7, then I can do technically I3 by A. No, I2. I can do I2 by A on this side. And it has two entries in the rows here and 2 entries in the columns here, which is why I chose the size I did. And 1 times 1 is 1, and 0 times 5 is 0, so we just get the 1 times 1, which is 1. 1 times 3 is 3, 0 times 0 is 0, so I still get 3. 1 times 2 is 1, plus 0 times 7, 1 times 2 is not 1. 1 times 2 is 2, plus 0 times 7, still 2. 0 times 1, and 1 times 5, well, we'll end up with a 1 times 5. 0 times 3 and 1 times 0, we'll end up with the 0. 0 times 2 and 1 times 7, we'll end up with the 7. So I'm hoping you can see what happened there. Because of the 0 in each row, we just end up with the first row. And this one, because of the 0 in position 1, we just end up with the second row. And actually, that's a useful way of thinking about this. This 1, 0 here tells me that I'm going to have 1 of all the things in row 1 and 0 of all the things in row 2. And so I end up just with row 1. And this one tells me that I'm going to have 0 of all the things in row 1 and 1 of all the things in row 2. And so I'll just get row 2. On the other hand, if I want to put a matrix on this side, it's going to have 3 things in its columns, because this has 3 things in its rows. And so now look at this. We have 1 times 1 is 1, and then 0 times each of these. And then I'm just going to go down the rows and do each column one at a time, if you don't mind. 1 times 5 is 1, and then 0 of each of these. Sorry, 1 times 5 is 5. Gosh. 0 times this, 1 times this, 2 times this. We end up with just 1 times 3. 0 times 5, 0 times 1, 0 times 7, we get 0. 0 times 5, 0 times 0, 1 times 7, we get 7. And I missed 1. 0, 0, 1. Okay. So I did it in a different order. Worth pointing out, you can do it in whatever order you want, but it's nice to be systematic so you don't miss anything. But did you notice what happened there? I tried to do it in a different order to actually show you what was happening, but I sort of failed there. But I'll show you now. When we did this column, we ended up having 1 times this bit and 0 times then, and 1 times this bit and 0 times them. So we ended up with this 1, 0, 0 produced just the first column. And this 0, 1, 0 produced the second column. And this 0, 0, 1 produced the third column. Pretty cool, and technically that was an I3. That idea of being able to pull apart matrix multiplication and do it 1 column at a time or 1 row at a time is useful, and it will come back at some point in the future if you ever study more matrices. And maybe you'll choose to study it because you want to find out what happens. I don't know. Not everyone's curious about that sort of thing. I am. Okay. So, what did I say? I said powers. All right. Now, you know how addition was kind of nice, but they had to be the same size, and multiplication was funky, and they really had to match up in exactly the right way. But they generally didn't have to be the same size. Powers are even more restrictive. Now, the only powers we're going to be able to do is whole number powers. So, we don't actually have a definition of what powers means for matrices yet. And we're going to have to borrow the original definition of powers for numbers and have matrix to the whole number is matrix times matrix times matrix times matrix. That's going to be our idea. We're going to borrow that. We're not going to be able to define what it means to have a matrix to the half, or at least not yet. For some matrices it's possible, but it's really, really difficult. And so we're not going to cover that here. So today, the only definition we have is we can have a whole number in the top. So a to the power of n is A times A times A, where there are n matrices. And this is for natural number n. And when I say natural number, I mean n equals 1, 2, 3, 4, etc. So I'm just actually going to pop that in properly. N equals 1, 2, 3, etc. And that's what it actually means to do that. So a squared is a times a, and a cubed is a times a times a, and that's all fine. But the only way you can multiply a matrix by itself is if it's a square matrix. Because the number of entries in the rows has to match up with the number of entries in the columns, and so you have to have the same number of entries in the rows as you do in the columns, so it has to be square. So it only works for square matrices. Okay. All right. And that's powers. Now there's a useful trick about the way powers work, which is that I can get to a to the 5 by first getting a to the 4 and then multiplying by a. And I know that sounds stupid, but it's useful in some of the proofs that we're getting at. Okay, so there are some rules for the way powers work, and they are basically exactly the same as the rules for numbers, because those rules for numbers were proved using this exact definition. So a to the I'm going to have to use letters. That n is confusing, isn't it? Because n is usually the size of the matrix. I'm just going to stick a different letter there if that's okay, just so that we don't get freaked out by everything being the same letter. Okay. Okay. So the rules are that a to the p times a to the q is the same as a to the p plus q. And that's just because there's p matrices multiplied here and q matrices multiplied here, so total number of matrices multiplied is p plus q. Totally works. There's another good one, which is a to the p then to the q is a to the p times q. That's a good one as well. And that's because, well, you've got a cubed. Maybe it's a cubed to the power of 4, a cubed, a cubed, a cubed, a cubed. And each of those is 3, and so there's 12 in total, and that's how it works. So you could prove them if you wanted, but we're not going to. So these are the general rules for how powers work for ordinary numbers. And we want to know how powers interact with the other things that we do with matrices, and how do they interact with addition, how do they interact with multiplication. And the general answer is they just don't. The only way for you to figure out how addition interacts, a plus b interacts with a power, is to literally multiply them all out using the distributive law that we already learned. There's just no call, you just can't do it, okay? Because matrices have that annoying thing that it matters which order they're multiplied by. And I'm actually going to do a specific example of that right now. But I'm going to add one more rule, which is back when we did it with numbers, we defined what, x squared or 3 cubed or 5 to the 7 was, and they were all very comfortable. And we were okay with something like 5 to the power of 1. You say, well, there's no actual multiplications, but there's only one 5 there, so that's okay. And then we also defined what to the power of 0 meant. Okay? And we are also going to do that with matrices. It's not nearly as productive as it is for matrices. It's easy to describe why. But by analogy, any number to the power of 0 is 1. which was the number that we multiply things by to not change them. So we are going to define matrix to the power of 0 to be the identity. Just because, and that's probably just not going to come up in most introductory matrix things, but it's just worth pointing out. We define it that way because we sort of imagine that this thing back here is the same as, we define it by thinking this, that a to the k is I times a times a, where there are k a's. Because well, you can always times by I, and it doesn't change the answer. So if we just change our definition just a little by putting an I times in there, then we can go, hey, cool, now if we don't have any a's, it's I. Fabulous. Okay. So I'm just knocking things off the desk here. So these are our rules. And this is how we think about this. So now I really need to do an example of using these rules in practice. So I'm going to do a neat little example of actually doing a bit of a proof, a little bit of an argument that you need to write down to explain why things work. And so I'm going to actually do it. Let's see. Let A be equal to this matrix. So it's 0 and minus a half and 2 and 1. It's a 2 by 2 matrix. It is a square matrix, so it will be possible to do powers of it. And I'm going to have show that a squared is the same as a minus I for this matrix. And then I'm also going to, this is part A, and part B is going to be show that a to the 18, well, just find it. Oh, damn it. I've forgotten to tell you a rule. Sorry about that. I'm just going to rub this out and get back to it. I forgot to see how powers interact with scalar multiplication, and they do actually. So more rules. If I have k a to the p, it comes out to the same answer as k to the p, a to the p. That's okay, because I know that there's just ka, 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 and all the k's can come out. And I also just need to tell you that ab to the p, that these are not the same thing. And that's because it's AB, 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 and because I can't rearrange the order, I just can't get it back into that. Okay, sorry about that. So let's do an example. Let A be equal to 0 minus a half to 1. Show that a squared is a minus I. And B, find a to the 18. So this is going to be a little example of how to do proper maths language while you're doing arguments using matrices. And we're going to have to use a lot of the rules we've seen so far. So let's see. A. Well, the only way I can show that a squared is equal to a minus I is to figure out what a squared is and figure out what a minus I is and notice that they are the same. So let's find it. A squared is the same as a times a. That's what a squared means. And what I'm doing is I'm calculating what a squared is, so I should start with a squared equals so that I can tell the reader that that's what I'm interested in. And a times a is 0 minus a half to 1. 0 minus a half to 1. And so let's see. 0 times 0 minus a half times 2 is negative 1. 0 times negative a half is 0. Minus a half times 1 is negative a half. 0 times 2 times 0 is 0. 1 times 2 is 2. 2 times minus a half is negative 1, and negative 1 plus 1 times 1 is 0. Okay, so that's what a squared comes out to. And let's figure out what a minus I is. Well, that would be 0 minus a half, 2, 1. And from context, the only way it's possible to calculate a minus I is if I is the same size as a. And so I'm going to must choose I2. So let's say 0 minus 1 is negative 1. Minus a half minus 0 is negative a half. 2 minus 0 is 2. 1 minus 1 is 0. And that is exactly the same matrix I calculated earlier. And so therefore I can say, therefore, a squared is a minus I. Beautiful. Okay, part B. Now, a to the power of 18, I could totally multiply a together 18 times and that would do it. It would take me a while. But I reckon I can make some guesses as to what's going to happen if I do a to the power of 18. I can at least start calculating what happens when I do a cubed and see what happens then. So a cubed is a times a squared. Remember how I said that might be useful? It's a times a, and two of those a's together are a squared. And I know what a squared is. It's a minus I. And a times a minus I, well, I'm allowed to do the distributive law. I can multiply this by both of these things, and so that would be a times a minus a times I. And I know that a times a is a squared. And I know that a times a is a because that's how I works. When you multiply by I, it doesn't change. Cool. Oh, and I know what a squared is. A squared is a minus I. So I can replace that. And look, a minus I minus a, well, I know that I can do subtraction in whatever order I want. And so a minus a is 0, the 0 matrix. And I know that the 0 matrix doesn't make a difference to addition or subtraction, and so I'm going to get minus I. So this is me using matrix algebra, and I don't have to actually multiply any matrices. I can just use the algebra to tell me what it is. So a cubed is minus I. I actually have an actual answer for a cubed without having to do any matrix multiplication. That's pretty cool. All right, well, if a cubed is minus I, then a to the 4 would be minus a, and a to the 5 would be minus a times a, which is minus a squared. And that, I could run through that pattern, and it would be pretty quick to get to a to the 18. But I have another plan. I know that if I do a power of a power, then that's the same as multiplying by the powers. And so let me think about what a to the 18 is in terms of a cubed. A to the 18 would be 3 times 6. That's what 18 is. And I know that the rules for powers say that that's a cubed to the power of 6. And a cubed, I know already, is minus I. And I have a rule for dealing with constant times matrix. That will be minus 1 to the 6 I to the 6, because that works when it's plain number times matrix. And minus 1 to the power of 6 is 1, because minus 1 squared is 1. And I to the power of 6, well, when I multiply I by anything, it doesn't change. So I times I should still be I, and I times I times I times I times I times I think that was 6, should still be I. And so this is 1 times I, which is I. So a to the 18 is the 2 by 2 identity, and just for completeness' sake, I'm going to write down the actual matrix that it is. Though technically, I probably didn't need to, because the person who wrote the original question knows what I means. So this is a little argument here that I was able to use the rules for how matrices work to calculate the answer for a to the 18 without actually doing any matrix multiplications. You'll notice that I have all these equal signs here because each step of this is equal to the step above. And so you would read this as a cubed is equal to a times a squared, which is equal to a times a minus I, which is equal to aa minus ai, which is equal to this, which is equal to this, which is equal to this. And then I wanted to say something about a to the 18, so I started with that and then figured out what it was. And I don't actually technically need to finish this with a therefore a to the 18 is 1001, But I could if I wanted to feel like it was properly finished. Okay. So let me just do one more example of just using matrix algebra, just to point out something useful. Expand a plus 2b squared. Actually, I might change that to a 3b so that we can see more easily what's going on. So expand means do all the multiplications you can, really. Make sure you don't write it with any brackets in it. That's what expand means. And so it's a bit of a vague instruction, but that's what it means. So a plus 3b squared, there's no rule for how powers interact with addition with matrices when the addition's down below in the base. And so I'm going to have to just use the definition of what squared means for matrices. And for matrices, squared means this. Okay? Now I know that matrix multiplication can be brought in over addition. So if I'm going to do this properly, I can imagine that this thing is going to get multiplied by both of these. Okay, so this a plus 3b has come to the left of both of these. And now I can do a little more now. I can bring this one in on the right-hand side, AA plus 3ba plus, and this can come in on the right-hand side, a times 3b plus 3b times 3b. Okay, so AA is a squared. There's a symbol for that. We have 3ba. This 3 can come out. We have 3ab. And 3 times 3 is 9b squared. And that's as far as I can go because AB and BA are not the same thing, necessarily. They're usually different. I am sure that A and B are the same size as each other. And the fact that A plus 3B squared is possible says that A plus 3B must be a square matrix, so A and B must both be square matrices. So AB and BA are certainly the same size as each other, but they are probably not the same matrix, so that's as far as I can go. Okay. Oh, these matrices, I mean, we've jumped into a new land where all these new things live, and we're trying to get as much information about them as quickly as we can. You're getting like the Lonely Planet guide to matrix land, and there's a lot of stuff going on. We've learned about the way that they behave, now there's two more things that they do that I need to talk about. So, two more things. One of them is a thing that numbers don't do, and the other one is a thing that's similar to what numbers do, but has to be really different for matrices. Okay, so the first thing I'm going to mention is called transpose. This is a thing you can do to matrices. The reason why we have it is because it sometimes makes our writing a little shorter. And there are some cool things that come up in some really fancy maths with transposes. But for today, we're just going to tell you what it does. So, transpose switches all the rows for columns. So, turns the rows of a matrix into columns and vice versa. If I really, and it's denoted like this, A transpose or possibly A little t. It doesn't really matter. Some people use a capital T, some people use a small t. Some people use a symbol that is very similar to a t but is a bit shorter, just to make it a little different to an actual t, like a perpendicular sign but upside down. But for most people it's just a t, t for transpose. And it looks like a power, but it is not. And which is why when we mathematicians write powers for an unknown number, we never put a t there because it stands for transpose. Though sometimes we do, and it confuses everybody. So this is how it's denoted, is the transpose of A, or sometimes just A transpose. And that's how it's denoted. And just so you know, the formal definition is that the ij entry of A transpose is the ji entry of A. And that's how you normally do it. But most people, you don't even think about it that way at all. They just do it. And so it's easier to just tell you. So what it does is it turns all the rows to columns, all the columns to rows simultaneously in one go. So if A was equal to this matrix, 3, 2, 1 and 5, 8, 7, 3, 5 in the first row, 2, 8 in the second row, 1, 7 in the third row, I can turn them all into columns. A transpose, this first row 3, 5 would become the first column 3, 5. This second row 2, 8 would become the second column 2, 8. This third row 1, 7 would become the third column 1, 7. Alternatively, you could have done it this way. The first column 3, 2, 1 becomes the first row 3, 2, 1. The first column 5, 8, 7 becomes the second row. The second column 5, 8, 7 becomes the second row 5, 8, 7. And that's pretty much all there is to transpose. Just point out that it can work on a single row or a single column just as much as it can on an entire matrix. And it works for any size matrix. And square matrices are particularly nice when you do transpose because they're the same size as they were before. I'm just going to write this down twice, just so that it's easier to see what I just said about rows and columns. So these 3 rows became these 3 columns. Alternatively, these 2 columns became these 2 rows. Okay. So, I mean, it seems like a pretty stupid thing to do, but there you go. That's what we've got. And it's actually really a nice thing because you can actually talk about how if you have 2 rows, then you can turn it into a matrix by going row transpose times column. So just as an example, if A was equal to 1, 2, 3, and B was equal to 5, 9, minus 2, then A transpose B would be 1, 2, 3, 5, 9, minus 2, which would be 1 times 5, which is 5, plus 2 times 9, which is 18, so 5 plus 18 would be 23, plus 3 times minus 2, which would be 23, minus 6, which would be 17. And so we can actually, with transposes, start to talk about everything in terms of columns if we want to. And maybe that would be useful for everything to really be a column and all rows are really columns transpose. That can be a useful thing in some of our algebra fancy stuff that we keep doing after we've learned all this stuff about matrices. Okay, so we want some rules. How does transpose interact with everything else we know? Here we go. So the first rule is if you do transpose and then you do it again, you get back to where you started. Like if you turn all the rows into columns and then turn all the columns into rows, then you're back to where you were. That's how transpose interacts with itself. If you do A plus B transpose, like you add them together and then you do the transpose, it's the same answer as doing the transposes first and then adding them together. And with multiplication, this is fun. Let me do scalar multiplication because that was the first thing on our list. So Ka, well, you can do the transpose first and then multiply by K. Makes no difference. If you're just multiplying all the entries and then switching them over, then that switching them over and then multiplying them is the same answer. So that's all good. And then matrix multiplication. This one's the funky one. You can actually do the two transposes of them separately, but it reverses the order. So that's pretty cool, actually. AB transpose, AB then transpose is the same as B transpose times A transpose, and you have to do them in the opposite order because the multiplication might not work in the other order anyway, for a start. But even if they were square matrices and they work both ways, it would still be a different answer if you didn't put them in the right order. And then what do we have next? Powers? Powers. That totally works. You can switch the t and the power and it'll work just fine. So that's how transpose interacts with everything. Now, it's not like I don't really need to do any examples of this right now. I just wanted to point out to you that I could do it. Every time I learn a new operation on a new kind of object, what I should do is try and figure out how it interacts with all of the operations I know so far. Because otherwise, what's the point? So I really should just do one example. Let's just make a random thing and see what happens. Let's see if we can expand that out. No idea. Just giving it a go. Oh, let's put a transpose on one of them. Aha, yes, let's do that. So there are some matrices A, B, and C, which somebody has decided what they are, and they're the correct sizes for this to work. And let's see what happens. Let's just practice doing the algebra. So we know that if we do transpose the way it interacts with multiplication, I have to reverse the order and do that. And I know that transpose interacts with plus this way. And I know that B transpose transpose is the same as B. And then C transpose A transpose plus C transpose B. I mean, and that would be like expanding this, right? Note that if someone actually gave me an assignment question that said expand this, it would not be appropriate to begin my working with an equal sign. Because that's just freaking out. It just says equals, like what equals? And so if you're going to do something like this, you really do have to copy it. Just so that the person reading it doesn't have to go back and find out what the thing it was supposed to be is. All right. So, how are we doing? Cool. So we've learned a whole lot of things that matrices do. Well, we've had addition, we've had subtraction, we've got multiplication, we've done negation, we've done multiplication, scalar multiplication, powers, and transpose. That's a lot of stuff. There is one more thing. Because what we haven't covered that numbers do, there's one more thing that numbers do that we haven't covered. We can't do roots. I already said that's not possible, so technically it is, but it's just really hard, so we're not going to do that. Because we can't do fractional powers. But what we are going to do is division. We haven't covered division yet. Numbers do division. Do matrices do division? And the answer is, sort of. Meh. First I have to wonder, what even is division? Like with numbers, yeah. Well, division sort of came about from a story where you sort of share things out with numbers. But if I'm thinking about them as pure algebra objects, what does division even mean? And when we sort of thought about that, we thought, okay, well, it's sort of like trying to find the answers to the question to a multiplication problem. And so that's what we're going to try and do. There is no division, but there is attempting to solve multiplication problems. Trying to figure out what the multiplication question is that produces a certain answer. Okay, so just an interlude. No, actually, I'm just going to do it. I'm actually going to say division. There is no division for matrices, flat out. But there is this. well, we can try to anyway. We can try to solve equations like, we can try to solve equations like that. So we can try to solve equations where we have matrix times an unknown matrix equals some other unknown matrix. Because that was what we used division for over with numbers. We can go, 3x equals 7, maybe 21. 3x equals 21, and we can divide both sides by 3 and figure out what the x is. Well, we can at least try and do this. It turns out that sometimes it's, there's either more than one answer or there's no answer, which is a bit distressing. So there are all these things that we can do to attempt to solve this, and there's a whole separate topic in this sequence of lectures about trying to use linear equation methods to solve that. But we're going to talk about one specific method, and which is the algebra idea, with what if there was something that we could do to both sides of this equation that would make this matrix here go away. That's what we would like. What if that was there? And back in numbers, it was division. That's what division could do. It could get rid of a multiplication. So we're going to create something, and the thing that we're going to create is called inverses. So what we want to do is we want to have, because there is no division, we can only do this with multiplication. We're going to think, what could we multiply here and here to make this matrix here go away? And it's not like you can really make a matrix go away, but if we could multiply something here to make this into the identity, then the identity times x is just x, and then it really would go away. So we're going to create an inverse, which is a new matrix, which when we multiply by the original one, produces the identity. The inverse of A is a matrix called A inverse. I believe the official word for called in maths is denoted by. Denoted by A inverse, such that A inverse times A is the identity, and also A times A inverse is the identity. And you may notice that it's possible for me to multiply A and A inverse both ways. And the only way that that's possible if A is a square matrix. So, though technically, no, that's right. Only way that's possible if both matrices are square matrices. So we can say only works square matrices. And even worse, it only works for some square matrices. So my powers only worked for square matrices, but they work for all matrices. Inverses are only going to work for some square matrices, and sometimes it can be a bit tricky to figure out whether it's going to work or not. And so we're going to need a rule for figuring out whether the inverse even exists. Okay. All right. So, that's great. I'll show you how we might use this before we actually show you how to do it. That's what I'm going to do. So let me do this example. Let A be equal to, give me a moment. So I just paused the video so I could figure out the question. And here I have, let A be this matrix, 3 over 2, 7 over 4, 2, 1. I did warn you that matrices are allowed to have fractions in them, and I have done it every so often. But today, here it is. And B is going to be this matrix, minus a half, 7/8, 1, and minus 3/4. So part A is going to be show that B is A inverse, and part B is going to be solve AX equals B. Okay. So to show that B is A inverse, well, the definition of A inverse is that whatever A inverse times A should be the identity, and so should A times A inverse. Now, there is actually a technical theorem that says that only one of those has to work for the other one to also be true, so you technically only have to check one of them. If you were giving me an assignment personally, I would be okay with that. But some people would prefer you check them both, so I'm going to do them both just to make sure that you believe me that it really is the inverse. So if B is A inverse, then BA should be the identity and AB should be the identity. So we'll calculate both of them. BA is minus a half, 7/8, 1 minus 3/4, 3/2, 7/4, 2, 1. So we have minus 3/4. Do you know what? I'm just going to write down these so that it's more forceful when it comes out to the right answer. It's going to be this nice little surprise and say, aha! So minus a half times 3/2 is minus 3/4. And 2 times 7/8 is 7/4. And then we've got minus a half times 7/4 is minus 7/8. And then we have plus 7/8. So we can already see it working. 3/2 and 2 times minus 3/4 is minus 3/2. 7/4 minus 3/4. And so 7/4 minus 3/4 is 4/4, which is 1. This is 0, this is 0, and this is 1. And so it worked. BA is the identity. And I should say equals I so that it matches with the formula that I wrote. And then B, no, not doing B yet. AB is 3/2, 7/4, 2, 1 times minus a half, 7/8, 1 minus 3/4. And I am going to skip the fancy bit that I did before. If I was being very nice, I would do it all. So that's minus 3/8. Oh, have I done something wrong? Yes, yes. 3/2, 7/4, 2, 1 minus that. Yep. Okay. So we've got minus 3/4 plus 7/4. We've already done that. That's 1. 21/16 minus 21/16 is 0. Minus 1 plus 1 is 0. 7/4, that's what I get when I do 7/8 times 2. 7/4 minus 3/4 is 4/4, which is 1, which is the identity. And so B is the A inverse. So if I want to solve this equation, it would be extremely rare to have to solve AX equals A inverse, but I'm just going to run with it. So we have AX equals B, and I don't have to actually do any matrix finding out what the entries of the matrices are right now. I know that if I multiply both sides by A inverse, on the correct spot, it will be next to an A and I'll be able to get an I. So I have two choices. I can multiply by A inverse here or here. I can do both matrices here on the right by A inverse. And that's not going to help because I'll have AX A inverse. And I can't switch the order of them, so I'll be stuck. But if I do it on this side, then it will be next to the A. And so A inverse times A is the identity. And I times anything is the thing. And luckily A inverse is B, and so I've got B times B. And so if I just calculate what B times B is, oh, it's going to be fun. that should be the answer. So minus a half times minus a half is a quarter plus 7/8. I'm just going to write that down because I don't feel like doing that fraction stuff in my head. That's be minus 7/16 and minus 21 over 32. Fabulous. Minus a half, minus 3/4, 7/8, minus, so 9/16. So whatever all of that is the answer. So 1/4 is 2/8, so we get 9/8. And 7/16 is the same as 14/32. And so we've got minus 35 over 32. Probably don't need the comma now. A half minus 3/4 is 2/4 minus 3/4. So minus a half minus 3/4 is minus 2/4 minus 3/4, so minus 5/4. And this would be 14/16 plus 9, which is 23/16, which is the answer. If I was very careful, I should probably check this by doing A times X is matrix times matrix equals this, and then confirming that it really is B. That's sort of how I would do the check, but I'm not going to do it. Yeah. And if this didn't work out to be B, then I know that something had gone wrong somewhere, probably in one of these fraction things, and I would go back and fix it. Okay, so great. That's the idea of what we use matrices for. And again, pointing out, very careful putting it on the same side that the A was. And I definitely can't put an A inverse here and an A inverse there, because I haven't done the same thing if I've multiplied the matrices in different places. I have to do them on the same side of both parts of the equation. Okay. So, right, I guess the last thing is, how do you find an inverse? Well, for a 2 by 2 matrix, the people who have walked this path before us have figured out a neat little trick that will tell you what the 2 by 2 matrix is, the inverse is. And for a bigger matrix, there's a trick, but it's not so neat that we can do. And there is one other question, which is, how do you tell if a matrix has an inverse? And there is a little calculation you can do on your matrix to decide whether it has one or not. And so I'm just going to do some things about this. So how do you tell if A has an inverse? And there's another word for this. A is invertible. So that's a good question. And there are two answers to it. One is attempt to find the inverse by the process that I'll be teaching you shortly. And the second is calculate this thing called the determinant. So the question is, how do you find an inverse? The answer is calculate the that's so badly written. The determinant. Now, the determinant is a thing that tells you whether you have an inverse. And for a 2 by 2 matrix, it's pretty simple. For a 3 by 3 matrix, it is less simple. Okay. So it's denoted by det A, like a function acting on the matrix, or by this, which looks like the absolute value of A for numbers, but it totally does not work that way for matrices. I'm going to run out of time. Totally doesn't work that way for matrices. So for 2 by 2 matrices, if A equals A, B, C, D like this, then the determinant of A is this calculation. Multiply this diagonal and multiply this diagonal and subtract them. So the main diagonal, the diagonal that I mentioned right at the beginning, the one that comes down from top left to bottom right, that one first, and then the other one, and subtract them. And if, denoted by this, if det A equals 0, it's not invertible, and if it's not 0, it is invertible. Okay, so that's for 2 by 2 matrices. So for example, my other matrix, well, any matrix I could care to consider, I could find the inverse. So for example, the first one that I wrote when I was talking about how this division thing works is 1730. The determinant of 1037 is 1 times 7 minus 3 times 0, which is 7, which is not 0, so this matrix is invertible. Okay. That's determinants for 2 by 2. For 3 by 3, they're a bit more complicated. And there's no real formula that I can write down in a way that makes sense in like a minute. And so it's just easier to show you how to do it. So for 3 by 3, I'll show you by example. Okay. So this matrix here as a 3 by 3 matrix. Remember, it only works for square matrices, so we're all good there. The determinant of this is figured out by turning it into a whole lot of 2 by 2 determinants. And you're allowed to, what you do is you go along a row or a column and you figure it out like that. So the determinant of A, the traditional way to do it is to go along the top row. So you take these entries in the top row and you have 1 and 0 and 2. And you do them as plus minus plus. Like that. And then what you're going to do is each of these is going to be multiplied by a smaller determinant. A 2 by 2 determinant. And the 2 by 2 determinant that you want is the one you get by crossing out the row and column that this number came from. So this one is here, and I cross out that row and column, and I get the matrix 1, 6, 0, negative 1. Some people call this a minor. Okay. This 0 came from this position, and the one I have is 1, 6, 7, negative 1. And this 2 came from this position here, and so what I have is 1, 1, 7, 0. And that's how to calculate a determinant. I'm not finished yet. I'm going to have to figure this out. I'm going to have 1 times negative 1 minus 0 times 6, because that's how you do a 2 by 2. Minus 0 times, I don't really care what this is. I'm not going to calculate it, because it's 0 times whatever that number is. Plus 2 times 1 times 0 minus 7 times 1, because that's how you do a 2 by 2. And so I get 1 times negative 1 minus 0, so that's a negative 1. The minus 0 is not going to make a difference. Plus 2 times minus 7, so I get negative 1 minus 14, which is negative 15, which is not 0, so A is invertible. And that's the traditional way to do it. Technically, you don't have to use the first row. You could use the first column. You could actually use one of the other columns as long as you kept track of where the pluses and minuses were supposed to be. My video recording is going to run out of time very shortly, and I'm not going to have time to actually show you how to find inverses. I'm very sorry. So there will be a second video at some point soon that shows you that bit. Unfortunately, the system I'm working on won't let me extend recording time. So I'm just going to finish off determinants while I'm at it. Technically, there is this plus minus plus. I can adjust that to be different if I use different rows. So let me just do something. I could also use any row or any column as long as I put the pluses and minuses in the correct spot. So I could use, for example, the second row. Now, that second row is going to have a different combinations of pluses and minuses than the one I had before. If I always have a plus in this top left corner, and I switch signs every time I switch positions, so plus to here would make that a minus, that would make this a plus, that would make this a minus. And so that's telling me the plus minus plus that I should have. So I will have minus 1 times a determinant from this position here, plus 1 times a determinant from this position here, minus 6 times a determinant from this position here. Okay. All right. So let's see. So this 1 here came from that position there. So I will cross that out. And the matrix I have left is 0, 2, 0, negative 1. This 1 was from the middle position, and I'll cross that out. And the matrix I have left is 1, 2, 7, negative 1. And this 6 was from this position, and the matrix I have left is 1, 0, 7, 0. Yep. Just enough space to fit it all in. And now I have minus 1 times 0 times minus 1, 0 times 2. I have 1 times minus 1, minus 7 times 2, which is 14. And I have 6 times 1 times 0, minus 7 times 0. That's nice. Most of those are 0. So that one's 0, that one's 0, and minus 1 minus 14 is minus 15. Same answer. Magic! And I'm just going to show you one more just to really ram home that it really does come to the same answer, and to show you something productive about being able to choose different rows and columns. Because you're going, David, if I can choose a different row and a column, why would I ever not choose the top one? And the answer is, if you choose one that's got lots of zeros in it, then your life will be easier. Watch this. What if I chose this column, which has 2 zeros in it? Because then, let's just see, there's a plus here, minus, switch over, that makes it a minus, switch over, that makes it a plus, that makes it a minus. And so we're going to get the determinant of A is minus 0. Sorry? I'm off the bottom of the screen, yeah. I can see it, you can't. It's going to be minus 0, plus 1, minus 0. Okay. And do you know what I should have done? Just a second. Now we can all see. The determinant of A is minus 0 times the determinant plus 1 times the determinant minus 0 times the determinant. And let's see, if I can do it with my fingers, I don't have to have a plastic sleeve. When I'm in this middle column and I cross out the first row, I get 1, 6, 7 minus 1. Not that I care because there's a 0 there. And if I'm in the middle column and I cross out the middle row, I'll get 1, 2, 7 minus 1. And if I'm in the middle column and I cross out the bottom row, I'll get 1, 2, 1, 6. And I don't care what either of these two is. And 1 times minus 1 is minus 1. Minus 2 times that's 14. And I get minus 15 there as well. So it doesn't matter which row or column I use, as long as I keep track of the pluses and the minuses, it should be okay. And that's how to find the determinant of a 3 by 3 matrix. If you are wanting to show someone really what you did, you could actually say, using the first row, using row 1, and then you could say using, this was using row 2, and on this one you could say using column 2. Just so that you could tell them in advance which row you're using or column you're using, so that when they look at your working, it's not so surprising what happened. So that is a calculation that we can do on a matrix. I have about 2 minutes to go, which means that I can now, we have just figured out a thing that we can do to matrices, which means that we should see how it interacts with everything else we know how to do. So let's see what happens. Addition, it's crap. We know it's not going to work very well with addition. So with rules, det A plus B, no idea. There are some very, very specific, special cases where you can figure it out, but most of the time it's like, nah, just add them together and figure it out. Det A times B, on the other hand, well, determinants sort of expand out over multiplication, which is sweet. That's kind of cool. And with powers, well, it works there too. That's nice as well. Transposes is fun. Determinant of the transpose is the same as the determinant of the original. Look, I told you could do it with rows or columns. Well, if it doesn't matter if you do it with rows or columns, then it doesn't matter if you switch the rows or columns either. And finally, what else was there? Scalar multiplication. This one's really interesting, actually. It turns out that if you multiply just one row by a particular number, then that'll multiply the whole determinant by that number. And the reason that works is, well, if all I did was multiply this row here, then that would have multiplied this number and this number and this number by a number. And that would have multiplied the whole determinant. So if you multiply an entire matrix by a number, you actually multiply the determinant n times, where A is n by n. What else we got? Inverses. The determinant of A inverse is 1 over the determinant of A, which is fabulous. All sorts of cool stuff going on there. And you can actually prove that, not too hard, by using this rule and the rule for how inverses work. And just one final thing.